So let's talk about curl and divergence. We're going to use the gradient, the use of gradient, and define curl and divergence. Let's see what we have. So our objectives: learn about curl and divergence. So I'm going to write down the definition, go over the example. Let F given as P, Q, R be a vector field. So we have a vector field. Gravitational vector field, we name it. Then we can define the curl as the gradient cross vector field F, and which gives you another vector function, and also the dot product between the gradient and the vector field, which result in scalar function. So this is a vector function, and this side, since you have a dot product, we get a scalar function. Okay. Remember that a gradient is defined as the partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. So we can define the cross product between gradient and the vector field using determinants. You have the determinant I, j, k. In the first row, remember that when we are working with cross products, order is important. Since the gradient comes first, you have to write down the elements or components of your gradient, which is partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z, and on the last row, we're going to list the components of your vector field, p, q, and r. So this is equal to I. We are taking the partial derivative of r with respect to y minus the partial derivative of q with respect to z minus j, the partial derivative of r with respect to x minus the partial derivative of q with respect to z plus, okay, now we are in the direction of z-axis, partial derivative of q with respect to x minus the partial derivative of p with respect to y. So we have a new vector function, and this is called the curl. So the divergence is not very hard to calculate. Here you just find the dot product between your gradient and vector field f. So here you have partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z, dot product PQR. Well, what did we get? We get partial derivative of p with respect to x plus partial derivative of q with respect to y plus partial derivative of r with respect to z. This is partial derivative. A couple of theorems. So let me write down the definition of curl and divergence here on the right-hand side. Then we go over a couple of theorems. So summary. Curl of vector function f is the cross product between the gradient F and F, and the divergence is the dot product between the gradient and F. So this is a vector function and this is a scalar function. So a theorem for you. Let F be a function of three variables. And suppose F has continuous partial derivatives. Then we can say that the curl of gradient of F is equal to 0. Note that if F is a conservative vector field, then the curl of F is equal to 0. So here's a question for you. Question. When we can say if the curl of F is equal to 0, then F is conservative. Theorem for you. Let function F be defined in the space with continuous partial derivatives. Then, if the curl of F is equal to 0, remember that when we are working with curl, define it as the cross product of the gradient and the vector function F. So you have to find the partial derivatives of F. So if partial derivatives are continuous, and if the curl of F is equal to 0, then F is a conservative vector field. Also note that by using this note, we can say that at this condition, if the curl is not equal to 0, curl of F is not equal to 0, then you can say that then F is not conservative. So these are the nice conditions that we can use to verify if we have a conservative or non-conservative vector field. Example. This example says, is vector field F, which is defined as xz, comma, xyz, comma, negative y squared, a conservative vector field? Well, you can say that, hey, since I learned a new topic, I'm going to check to see if the curl of f is equal to 0 or not. So let us use curl of f. So this is defined as I, j, k, partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. The first component is xz, the second component is xyz, and the last component is minus y squared. Well, I have I. The partial derivative with respect to y is negative 2y, minus the partial derivative with respect to z is xz, minus j. The partial derivative with respect to x is 0. The partial derivative with respect to z is x, plus k. The partial derivative with respect to x is yz, minus the partial derivative with respect to y, which is 0. So as you can see, here you have minus 2y, minus xz, comma x, and here you have yz, which is not equal to 0, 0, and 0. So it means that it doesn't satisfy the condition of curl equal to 0. So you can say that since curl of f is not equal to 0, then f is not conservative. Another question, another example for you.
Professor, could you keep it for a moment? Thanks.
Sure. So we have another vector field. Now we check to see if we have a conservative vector field or not. So is vector field f, which given as y squared z cubed, comma 2xy z cubed, comma 3xy squared z squared, and it has x next to it. Conservative vector field or not? Well, take a look at the components of this vector field. All of these components are in the form of x, y, z. You see multiplication with positive exponent. All of these are nice elements, nice expressions. So if you take the partial derivative of each of these, all of them are continuous. And note that if you think about the domain, you can just say that, hey, this vector field is defined in this space. You don't have to restrict anything. So let's find the curl of vector field f. The cross product between the gradient and the vector field. I, j, and k. So partial derivative with respect to x, here we have the operator. Partial derivative with respect to z, and we get y squared z cubed, 2xy z cubed, and here I need more space. K, partial derivative with respect to z, and 3x y squared z squared. Well, I have I. So partial derivative with respect to y is 6xy z squared minus partial derivative with respect to z, 6xy z squared minus j. Well, partial derivative with respect to x gives me 3y squared z squared minus partial derivative with respect to z, 3y squared z squared plus k, partial derivative with respect to x, which is 2y z cubed minus the partial derivative with respect to y. Here you have 2y z cubed. Okay, as you can see, the first component is 0, the second component is 0, and the last component is 0. It means that the curl is equal to 0. Curl of f is equal to 0. This is not just scalar 0. This is vector 0. So this is vector 0. So since the curl is equal to 0, we say that we have a conservative vector field. It means that we can find a potential function for that.